Okay, so now we're going to carry on with chapter 6, and where we left off was after introducing the basic properties of the normal distribution, we're going to see how to calculate normal probabilities with Excel and with a calculator. Okay, so the two basic functions in Excel are called norm.s.dist and norm.s.inv. Now, at the moment, these mean nothing to you, but both of those also appear in here, but we'll see how to use those in a bit. So here's what we want to do. So we've got two spreadsheets here, and the first one is called simply Chapter 6 Examples, Part 1. Actually, that's the wrong one. Hold on. Yes, here it is. So what we're going to do is learn how to calculate normal probabilities with Excel. Now, I do remember the other day I mentioned that the normal distribution the distribution has a bell-shaped curve. The two values that uniquely identify it are the mean and the standard deviation. Okay, the mean is in the center, of course, and as you saw in the last session, the standard deviation determines how spread out the curve is, but no matter how spread out it is, it still takes the form of this bell-shaped curve. It could be a very tall bell-shaped curve or a very flat bell-shaped curve, but it's always a bell-shaped curve. Okay, and also don't forget that it goes all the way out to infinity on the upside and negative infinity on the bottom. Also, it's symmetrical about the mean. The entire area under this curve is equal to 1 because that's the probability. And then on either side of the mean, we have a probability or area of a half. So with all that being said, we also remember there's one special case, the so-called standard normal distribution. Is the one where the mean is 0 and the standard deviation is 1. And also don't forget that this is the unique case where we use the letter Z to represent it as opposed to X, which is used for all the rest of them. Okay, so that's how you can tell just by looking at the fact that there's a Z here is a reminder that this is the standard normal distribution to distinguish it from all the other cases. Okay, now here what they want us to do is take this standard normal distribution, and first they're going to have us calculate the probability that Z is less than or equal to 1. All right, so what would that look like on the graph? No, I've written it like this, but we could also write it like this. But it's understood that the lower limit is negative infinity, so we don't really have to do it like that. If you write the probability that Z is less or equal to 1, it's understood that it goes all the way down to negative infinity. So how do we figure this one out? Well, the command that we need in Excel is called norm.s.dist. The S, by the way, stands for standard, to make sure it's clear that you're dealing with the standard normal distribution. And then if you notice in this little ribbon here, it asks you for a Z, which is 1 in this case. And then it asks for this cumulative value, which we've seen before. Cumulative means less than or equal to. If you put a 1 here, that means you do want cumulative. If you put a 0 here, you do not. With the normal distribution, we always say yes to this one. In other words, you always put 1 for cumulative anytime you're dealing with the normal distribution or the standard normal distribution. Okay, so let me put a note here. By the way, if you notice, it did not show me the result because it's in a special mode. If you hit the keys Control and then hit the tilde button, which is that strange little symbol just to the left of your one key, that command will flip it back to show you the results instead of the formula. Okay, so in other words, if you keep flipping back and forth between Control tilde, this way I'm seeing the formula, this way I'm seeing the answer. All right, so it's a very handy tool to go back and forth so you can see, and it also shows you the entire spreadsheet. There's other commands for single cells. This is just for the entire spreadsheet. So remember, Control tilde, whether you have a Mac or PC, it's the same. This is one of those rare cases where the commands are the same on both a Mac and a PC. And also Control, I think, is the same in both anyway. I know that some of the others are different, but anyway, so we always let cumulative equal 1 with a normal distribution, which is not the case if you remember from binomial and Poisson. There we only use it if we mean less than or equal to. Here, because of the way the normal distribution is defined, we only use the less than or equal to case. Okay, so even though it offers you the option of having 0 there, you don't take it. All right, that's for something completely different, which we will not be doing in this class. And also, again, if you didn't see, it's norm.s.dist. Now, the S in that command means standard. Okay, so we're using norm.s.dist, standard normal distribution. Use this for computing probabilities. All right, so that's how that works. Now, here's an interesting one. We need to find the probability that z is somewhere between negative a half and positive 1.25. Now, what does that look like in the graph? Okay, so in other words, it's somewhere in between negative 0.5 and positive 1.25. Now, here's where it gets a little tricky. The Excel command is not set up to do in between probabilities, so we have to work around it. This is our basic logic. We're going to find this by doing the following. So in other words, both of those commands are in Excel. This one would be norm.s.inv of 1.25 and 1. Remember, the second command will always be 1 for cumulative. And then this one will be norm.s.ind negative 0.5 and 1. And so what I'm going to do is subtract, okay? Algebraically, all I'm doing is subtracting one area from the other. What's left over is the part in between. So the Excel command will be norm.s.ind 1.25 comma 1 minus norm.s.ind negative 0.50 comma 1. All right. So in other words, even though Excel doesn't actually have this command built into it, we can work around it by doing it this way. And that's probably one of the reasons why the command's not in there. They figure, why waste a command on something you can do yourself? So it's here, norm.s. Keep in mind, by the way, that when Excel was first invented in the 70s, computer memory was horribly expensive. So anytime they had a chance to save by leaving out unnecessary commands, they would do it. Okay. Now it's different. Computer memory is a lot cheaper. But back in the day, in the 70s, it was dreadfully expensive. So you can see they had to make a lot of choices. All right, so this is exactly what I wrote in the notes. And let's see what that equals. So, um, norm.s. Did I make a typo? Okay. There it is. There we go. Okay, so this is what I did. Now, based on that logic, that number three, you'll notice we're looking for the probability that z is between negative and positive one. So we're going to take the exact same approach. All right, so based on what we just did, it should be clear that we're going to do this. Norm dot s dot in norm dot s dot dist one comma one minus norm dot s dot dist. Oh, wait a minute. What did I do? You know what I just realized? I wrote the wrong thing up here. Um, oh my God. Sorry about that. I don't know what I was thinking of. This is dist. We don't know what IMV means just yet. I apologize for this. This is dist. This is dist. We'll see in a few minutes what in INV is for. All right. Yeah, it's been a long semester, right? Yeah, sorry. These are dot dist. Yeah, I tell you what, the reason maybe why that happened is because the function on the TI 84 looks more like this. But all right, anyway, so same thing here. It's dist. All right, let's see what that is. Now, I would like to point out something to you interesting. Earlier, we looked at this so-called empirical rule. And if you remember, this is actually one of the cases that it mentions right here. Here it is right here. So with the empirical rule, which is, remember, these are only approximations. This probability, and by the way, keep in mind, this empirical rule applies no matter which distribution we're looking at, no matter what the mean is, what the standard deviation is. So in other words, this applies to all normal distributions. Being within one standard deviation of the mean has an approximate probability of 68.3%. So the case that we just looked at, although it may not have been super obvious, this means Z is within one standard deviation of the mean because And I'll write that here in the notes too. With a mean of 0 and standard deviation of 1, 0 means we're at the mean. Z equals 1 is the same thing as saying 1 standard deviation above the mean. And then -1 would mean this. And that, of course, would indicate that we are 1 standard deviation below the mean. So with the standard normal distribution, the numbers you're using actually represent the number of standard deviations above and below the mean. We can interpret them as how many standard deviations we are away from the mean. And that's one of the reasons why it's so useful. It can be very helpful. With these, we need to know the actual data. We need to know the mean, the standard deviation to determine the actual numerical value of mu minus sigma and mu plus sigma. But here we don't have to worry about that. It's just automatically plus and minus 1. So you have the graph. So the actual value here that we just got through calculating in Excel, rounded to 4 places, is 0.6827. The empirical rule tells us that it's 68.3%, which you can see is very, very close to the actual value. Okay, so if you only need an approximation, you can use the empirical rule, but only if it happens to be in this form. Okay, for all the others, we have to do it ourselves. Okay, great. Oh, one more detail. Yep, I've mentioned this many times before. It really drives me at the wall that with Word, you have to remember to put in your own page numbers. It doesn't automatically assume that, which is so ridiculous. But anyway, then we have one more. Now, this one is different because Z is greater than or equal to 158. We haven't tried that one before. And again, Excel does not have this command. We have to work around it with our knowledge of how this normal distribution works. All right, now remember the curve itself has a total area of 1. Okay. So the shaded area to the left of that uh, this. Now, between the two of these, they cover the entire curve. So the result of this is that it's important because this is how we're going to find this answer. Algebraically, this is the same thing as Okay, so in other words, I subtracted the probability that z is less than or equal to 158 from both sides. And the reason why I did that is because this I can solve for in Excel. Um, Using the norm s dist, make that a little neater. So whatever the difference is what we're actually looking for, which is z greater than or equal to 1.58. Okay, so let's try that. And this is our final result. So for all less than or greater than or equal to probabilities, um, use this approach. Okay, notice no matter what the situation is, greater than or equal to is not in Excel. So you have to do it this way. All right. So now we've got our hands on some Excel commands. And so this is okay. So let's see what's coming next. By the way, if you look in the slides, you'll notice how the second command is true. I just want to remind you that in Excel, when it asks you like for a value that's either true or false like that, um, in Excel, one equals true, zero equals false. So you can feel free to type the word true or false if you'd rather, but just be aware one and true mean the same thing. Now, and there's the answers, same as we got, of course. Um, Whoops, wrong one. 8413, 5858, 6827, and 0.0571. Oh, another thing I want to mention here is by convention, probabilities are usually rounded to four places, unless they're extremely small. If you have a huge number of zeros, then you might use more, but normally probabilities are rounded to four places. So that's why you notice all four of these. I already set it up in advance to have four places. All right. Now this one is a little different because we're going to reverse the process that we just followed. So let's see what this is all about. So it says Z value with 0.10 in the upper tail. What does that mean? So it's some value of Z such that the area above it is 10%. Whatever it is, the area below it is 90%. Okay. And by the way, sometimes the value of Z in these problems is often referred to as a Z-score. You may have heard that phrase before, Z-score. This is what they're talking about. Just any value under the standard normal curve is known as a Z-score. So we need the Z-score such that the area above it is 10%, which implies that the area below it is 90%. So how do we find this Z-score? Well, that's where this command comes in. Norm dot s dot inv, and the probability, surprisingly enough, is not 0.10, It's 0.90. Why? Because it's set up to look at the area in the left tail. Okay, so in other words, we use norm dot s dot inv, and here it just asks for the probability, which means in the left tail. And we discovered that it's approximately 1.2816. Now, if you're skeptical that you did this correctly, what you could do is double check like this. And you go back to Excel and you say, well, what is that probability? Oops. No, not the 0.9, the 1.2816. And except for potentially any rounding issues, there it is. If you want it to be exact, you do it like this: norm dot s dot dist of this number, whatever it is, and then you put the 1, and there it is, 90%. Okay, so that's what this is all about. We're finding a z-score that corresponds to a specific area in the two tails. Now, this next one is 0.025 in the upper tail, so it'll be very similar to this one. And remember, those two have to add up to 1. Okay, that's where that's coming from. In other words, if there's 2.5% in that right tail, then the rest of the distribution is 1. So we're going to use the command to come up with what we're looking for. Remember, use the left tail in that command. Norm.s.inv 0.975, 1.96. And remember, that means mean plus 1.96 standard deviations, or 1.96 standard deviations above the mean. And again, we can do a double check. As a matter of fact, I can just drag this down, and there it is, because what it's asking for is the norms.dist of this number and 1. Now, this third one is a little different because if you notice, they're looking for the lower tail, the 0.025. Okay. So we're already in the left tail, so you use the command oh, actually, sorry, this one doesn't need a 1. Just 0.025. And whatever number we get, it's going to be negative because we're below the mean, okay? Because it will be a certain number of standard deviations below the mean. So the command is norm.s.inv 0.025. And interestingly enough, these two are the same number except for the magnitude. And there's an obvious, I mean, there's a very good reason for that. It's because Because of this property of symmetry. Okay, remember the left and the right-hand sides of this distribution exactly match each other. This is true because the distribution is symmetrical about the mean. So that's why the one and positive 196 and negative 1.96 are the same. Oh, I just realized I put a negative here. This area is not negative, sorry. This is 025 and 025. It's the same area, but the z-scores are positive 1.96 and negative 1.96. Okay, well, that was interesting. So that was part one of this sheet. So what's next? A problem. Now, there's another spreadsheet for this, I believe. Oh, maybe not. Actually, I think we have to do this one algebraically. Now, what they've done here is they've put a table in here. There does exist a table which is designed to help you calculate standard normal probabilities. It's in the back of the book somewhere, but with the calculators, you don't really need it. Before calculators came along, this is how people calculated normal probabilities. But now we've got, the calculators and we have Excel. But here they're using it just to illustrate that this is how a table would work. So they've got the Greer Tire Company. They have a new steel belted radial tire, and they want some information about how far the tires are going to last, how many miles. So they want to know, let's say they're trying to figure out where to set the warranty. They want to know, like, for example, if they give the customers a warranty for X miles, they want to know what proportion of the customers will actually be able to take advantage of it. It'd be good to know that before you give out a warranty. Those numbers they offer you are not just taken out of thin air. They know from experience how likely it is that you're going to actually cash that in. So let's just say that they know from experience that these tires have a mean of, oh, by the way, let's take a step back. We're assuming that the ages or the mileage that we get out of these tires is normal. That's it doesn't actually say that, but it's understood because this is in the normal distribution section, but they should really specify that the tires mileage is normally distributed, and then they have to tell you the mean and the standard deviation. Okay, so this is our tire example. All right, so once again, we're assuming the tires have a normal distribution. The mean is 36,500. The standard deviation is 5,000. So your curve would look something like this. And then you could put in here, for example, one standard deviation above the mean would be 41,500, and one below would be 31,500. And that's what your distribution roughly looks like. So the question is now, what's the probability that a tire is going to last more than 40,000 miles? So let's say they're thinking about choosing that as the warranty. And so, in other words, now, by the way, we're using the letter X again. X is the lifetime of a tire. The mean, again, is 36,500. The standard deviation is 5,000. So if you're going to use that table, or if you're just going to use the standard normal distribution, what we're going to need to do is this. And so I mentioned this formula once before. We didn't really use it. And so what it says is, well, whatever X you're looking for, you can convert it into a standard normal random variable by subtracting the mean and dividing by the standard deviation. So here you'd have 40,000 minus 36,500 over 5,000. And that's going to tell me how many standard deviations away from the mean I am, which I can then use to calculate this probability. Okay, it's 0.7. So basically, you can now draw this curve like this. In other words, so that's what that's all about. So now, if you wanted to, you could go do this in Excel. Now, what they're going to do is show it to you with the table. Now, this table only has less than or equal to probabilities. So what you have to do to find this on the table is you're looking for the intersection of 0.7 and 0.00 because that adds up. And so it's right there, 0.7580. And that tells me that the probability that Z is less than or equal to 0.7 is 0.7580, which means that in turn, the probability we're actually looking for uh 2320. So approximately 23.2% of the tires should last at least 40,000 miles. Oh, sorry. That's what I get for doing it in my head. It's 2420. Now, of course, we know how to do this in Excel. In Excel, what you would have done is this. Okay, in fact, we could prove it. Let's come over here to Excel. Although it's not part of this spreadsheet. Well, let's throw in a third sheet just to prove it. Yeah, so it's slightly we could change this to 4 digits. It's yeah, there you go. Now, here's the interesting part. If we're using Excel anyway, we don't have to actually convert to the standard normal form. What we could have done instead is this. X is the mileage of the tires, or I'll just call it tire mileage. Remember, they told us that the mean is 40,000. No, it isn't. Sorry, it's 36,500. And the standard deviation is 5,000. And then they wanted to know the probability that X is greater than or equal to 40,000. So you're probably saying, well, how do we do that in Excel? Well, there's two complications here. Number one, we're using X instead of Z. And also it's a greater than or equal to probability. So we'll do it in 2 stages. We'll start here with less than or equal to 40,000. And so here the Excel command is slightly different. Instead of norm.s.dist, it's norm.dist. dist without the S. But now, in addition to the X, we have to tell it the value of the mean, the standard deviation, which I'm going to use cell references for. And remember that one there, don't forget the one. And so that's the probability of being less than or equal to 40,000, which means to get the probability of being greater than, it's 1 minus this probability. There you go. So in other words, Excel can handle any normal distribution. The standard normal gets the S, the rest of them have no S. That's how you can tell them apart. So if you're using tables, which is what was done before Excel and calculators came along, you have to convert to the standard normal because that's the only table we have. But for any other situation, we can just do it directly, okay, as I just showed you. So the tables are not very important anymore, but you can still use them if you want to. All right, now, what remains here is, let's see, what else do they have here? Oh, they're going to have us do this all in Excel. And then what I'm going to do before we forget, I'm going to go back and show you how to calculate all these probabilities with the TI-84. Okay. They didn't do that in the slides for some reason. They just show you the Excel, but I'm going to show you the TI-84. But first, they have an extension to this problem. And what they're saying is, listen, what if we want to make sure that whatever warranty we choose, no more than 10% of the customers will ever take advantage of it? So that means that we're going to use the inverse process again. And so what they want us to do is this. Back to this example. We need to find the number of miles, or X, such that no more than 10% of the time does the mileage go past that point. So what they're going to recommend we do here is they want us to convert everything back into the standard normal form. So that means the mean here in the standard normal form would just be 0. And then whatever point we're looking for, it represents 10% of the distribution. So their recommendation is to do this. We're going to take that formula we had a few minutes ago. We're going to rearrange it algebraically to solve for X. Okay. Okay, so by plugging in these numbers, oh, by the way, in order to do this, what we also need is this. We need to find the z-score that corresponds to a right tail of 10%. Now, we actually already did this before in Excel. That's probably why they chose that one. Remember, just a little bit, here it is, 10% in the upper tail, 1.2816. And we're going to need that for this formula. All right, so 5,000 is the standard deviation here. I think they're rounding it to in the slides to 1.28. Let me just confirm that. Yeah, so let's just stick with that 1.28, even though that's, it's been rounded. So you take out the calculator. And that is 42,900. So what this implies is that 10% of tires will last more than 42,000 miles. Okay. So therefore, oh, I just realized I no, there's a wait a minute. Oh, I think I misinterpreted what they wanted. They wanted the lower 10%. Oh my God. I misinterpreted what they were doing. They no, sorry, they wanted the bottom. So that means we're down here. I guess I didn't read it carefully enough. So that means that we have to change this to negative 1.28. And that means this number is going to be different, obviously. Yeah, it's 30,100. So that means that 10% will last less than 30,100 miles. So basically, what they're saying is that if they set a warranty at 30,100 miles, they're guaranteeing you'll get at least that much. That means at most 10% of the customers will bring their tires back to be replaced because they lasted less than 30,100 miles. I guess that won't bankrupt the company. That's their interest in all this. Like, how many tires do we have to replace? We can probably afford 10%. So we'll choose a warranty number of tire miles that will not bankrupt us by only requiring 10% to be replaced. All right. Now, oh, all right, let's finish this part and then I'll show you how the calculator works. They're giving us in this next sheet some probabilities. And so we've already kind of touched on this. The probability that X is less or equal to 20,000, given that oh, it's the same problem. So the mean is 36,500. And the standard deviation is 5,000. Okay. So great here. So we're going to have norm dot dist without the S. The X is the 20,000. The mean is 36,500. Whoops. Don't try to resist the temptation to put commas in there, except to separate the numbers. The standard deviation is 5, and the cumulative is always 1. Okay, and then there we go. Now that's 0.0005. Yeah, that's because that's quite a few standard deviations. That's like more than 3 standard deviations below the mean. And that's a very, very rare occurrence. Then we have an in-between problem. Now remember how this works. We're going to do norm.dist of 40,000. The mean is 36,500. The standard deviation is 5,000. Don't forget the 1. And then we subtract from that norm.dist 20,000, comma, 36,500, 5,000, 1. All right, and then for greater than or equal to, we know how that works too. It's 1 minus norm.dist of 40,000, 36,500, and 5,000. Plus, don't forget the 1. All right, so those are fine. Now, these are the ones where you're looking for a specific area with a given tail, right tail or left tail. And so for these, you're going to use norm.inv. Notice again, there's no S here. So keep in mind, if 10% is in the right tail, we need the left tail, 0.9. But because this is X, we also need to specify the mean and the standard deviation. This one is, oh, look, I did it again. I misread it. This says 10% lower tail. So we change this to not 0.9, but 0.1. That's better. Okay. Yeah, so I didn't read it carefully enough. It was 10% in the lower tail, so this is 0.1. This one is the upper tail. So that means we're going to have the probability will be 0.975, but then we have a mean of 36,500 and a standard deviation of 5,000. And we can round these. Here's how you do that. Go up here to number. I think they only need integers anyway for this problem. Oh, maybe they don't. They want 2 digits. What do you know? Okay. Let's put them back so you can see everything worked out beautifully. All right. Now, oh, there's more. Oh, no, that's the next distribution. That's the exponential. We're not going to get to that for a bit, because what I'm going to do now is show you how to calculate normal probabilities with your calculator. All right. So let's see. So it doesn't take that long to get used to this. It's fairly straightforward. There's just 1 or 2 quirky things you have to know. So we'll start with the standard normal distribution. So let's just say we'll start out with a simple one. Okay, so you go to the calculator and you start with second vars. Now, remember, this is how we got started looking for the Poisson and the binomial distributions. Except now you might be surprised this time that you're going to pick normal CDF. Now, keep in mind, that's because all these probabilities with the normal distribution are always less than or equal to. And C stands for cumulative. So C means less than or equal to. So with Poisson and binomial, you're using PDF. for individual probabilities. Here, we don't use individual probabilities. So instead, we use CDF because it is cumulative. Now, if you notice, it needs to know four things. Now, remember, I did mention before that the lower limit here technically is negative infinity. Well, here you do have to specify that. So it's going to ask you for four things: lower limit, upper limit, mu, and sigma. These are, of course, 0 and 1 because this is the standard normal. Now, for these, the lower limit is actually negative infinity. The upper is 1. There's just one wrinkle. The calculator doesn't actually have a negative infinity key. There's a workaround, though. What you have to do is type negative second, comma, 99. And if you do it correctly, you'll see in the window negative E, oh, it's capital E, negative E99. That actually means negative 1.0 times 10 to the 99th power. It's not negative infinity, but it's getting close. So that's how you're going to calculate or implement negative infinities on your calculator. So why don't you go ahead and type that in, and let's see what we get. Now, we actually solved for this once before, and it turned out to be 0.8413. All right. So, of course, the same thing is true here, except that, it's giving you more digits, but we're rounding. Remember, the convention is 4 places. Well, all right. Now, you're going to be happy with what I'm going to show you next. With Excel, we would have to do 1 minus norm.s.inv. Here, we don't have to bother with that because here's what we'll do instead. Just change the lower and the upper limits. These won't, by the way, these you can just leave them there. They won't change unless you change them yourself. The lower limit now is 1. The upper is positive infinity. And that's going to be represented as simply second, comma, 99 without the negative. This is replaced in the window with E99. So why don't you go ahead and fill that in, and let's see what you get. Rounded to 4 places, it's 1587. Now, if you look carefully, you'll notice we just did 2 probabilities that are related to each other. This is greater than 1. This is less than 1. So the first one we did was the 8413, less than or equal to 1. Now this one is greater than or equal to 1, which gives us 0.1587. We actually could have done this directly because we know that these two have to add up to 1. All right, so in other words, this is And there you go. How do you like that? Okay. Now, what about in between probabilities where we had to subtract with Excel? Again, we don't have to bother with that here. We can do it directly. So let's do number 3. So this time we're going to find the probability that Z is between negative and positive 2. And of course, the last 2 terms are the mean and standard deviation. So if you plug those in, rounding to 4 places, you will get by the way, this is one of those cases where you do not need either positive or negative infinity. 9545. And this, by the way, don't forget that old empirical rule. This is being within 2 standard deviations of the mean. And for that, they gave us as an approximation. Here it is, 95.4%. Okay. It's actually 95.45%. So that empirical rule is not too terrible, is it? It is not. Now we're going to try 3 cases where we're using X instead of Z. Okay. So this is the normal, but not standard normal. So let's say X is normal with a mean of 500 and a standard deviation of 100. So we start by calculating the probability that X is less than or equal, let's say 400. All right, so we go to the calculator. Oh, whoops, sorry, that's not right. That doesn't go in the middle. 500 goes in the middle because that's the mean. All right, so the lower limit is the negative infinity. The upper is 400. Now here, be careful. The mean is not 0 anymore. It's 500. The standard deviation is 100. So make sure you change those. All right, let's see what this gives us. Uh, 0.1587. Okay. Now, if you notice, let me just show you one interesting result here. This is the mean, and this is one standard deviation below the mean. If you remember, we did this exact same problem with the normal standard normal distribution. So they have to be the same, right? So just a few minutes ago, we did, or maybe it was at another, yeah, well, sometime tonight, we've definitely done this one. And it was 1587, but I just want you to see the connection between the two. Because here's the thing, the probability doesn't depend on the numbers, actually. It depends on the number of standard deviations we are away from the mean. That's the bottom line. All right, then let's try this one. The lower limit this time is 600. The upper is infinity, which is the same thing as second comma 99. The mean stays at 500. The standard deviation is 100. And so when you plug those in, it's, what do you know, 0.1587. Now, if you notice, we're starting to see this number a lot. It's not a coincidence because of the symmetry of the distribution. That's how this happened. And then C, let's try this. All right, so we don't need any infinities here. All right, let's see how that works out. 0.6827. Now, again, we could have figured this out with our knowledge of this distribution. Because, and except for some slight rounding differences, this area in between must be one minus the two tails, which gives us 0.6826. So the difference is rounding. Okay, and also back to that empirical rule, what you're seeing in the middle here is being within one standard deviation of the mean. Okay. All right. So now we are experts in using our calculators with the normal distribution. So what remains here in this chapter, chapter 7, that is, sorry, chapter 6, is the exponential distribution. Now, this one is used for certain cases where it's actually related to the Poisson. Poisson says, let's observe the passage of time and calculate the probability that a certain number of events occurred during that time interval. This one flips it around and says, what is the time until the next event occurs? Okay, so in other words, if you're watching cars go through the intersection and you say, what's the probability of getting three during the next hour? Here, instead, you might turn it around and say, what's the probability that it will be 20 minutes until the next car? So, interestingly enough, the Poisson is a discrete random variable. This one is continuous. So the formula isn't really very complicated looking. Look at that. You can definitely solve for this directly. You can do it as a probability or what's called a cumulative probability. And let's see. And luckily, as it turns out, this is built into Excel. So let's quickly wrap this up. And this is in our spreadsheet, by the way. This is the last tab in part two, rather. Ah, there it is. Okay, so let's just quickly run through this. We have, this is the formula we're going to use. This is our less than or equal to probability. And, this one, I was saying this before, I think this one, it's not that important, but compared to the normal, the normal is used constantly in statistics. This one is only used for very special occasions. So this is the one we'll be using most of the time. By the way, mu is mean, just like it was in the Poisson distribution. Okay, so for example, we have trucks loading at the dock. The mean or average loading time is 15 minutes. Okay. What's the probability that a truck will take 6 minutes or less? Wow, that would be pretty impressive. So this X0 is the 6. Okay. So look how simple this is. Now, of course, 6/15 is equal to 0.4. Now, this function, by the way, does not appear in your calculator. They only have so much room in there. It's more of a problem for a calculator than for Excel to have, there's only so much room you can put into something this size. So they chose not to include that one, but it's because this one is so straightforward to do directly from the formula. So if you plug this into your calculator, you'll get 0.3297. That's it. That's all you have to do. Now, what about Excel? Excel's version is here. We're going to try 3 of these. Now, just like with the other cases, with Excel, it only normally includes a less than or equal to function. The others we have to do ourselves. So we're going to come back here and let's see, what are we doing here? So X less than or equal to 18. Now, remember too, here, it looks like it's the same problem where mu is 15. They should have specified that, but all right. So it's exponent.dist. X is the 18. Oh, now here's where we have to watch it. It's like there's always something. It turns out that Excel's function is a little different. They have a value in here called lambda. which is 1 over mu. So if you notice carefully, if you notice when it was asking for information, um, or actually, let's come over here and look at it. Lambda is the inverse of mu. I don't know why they chose to do it this way, but they did. So when you enter this into Excel, you have to keep this in mind. Don't put 15 there. It's 1 over 15. That's the only quirky thing you need to know here. Then, now this one, we have to do the in-between thing. In other words, exponent dot dist. X is 18, lambda is 1 over 15, cumulative is yes. Then we have to do the same thing for 6 and subtract. And then finally, greater than 8, that means 1 minus exponent dot dist. 8 and 15, 1. Okay, so that lines up with theirs. 4 places, and we are all set. Okay, so now that, by the way, that's it for chapter 6. And oh, here's the graph of what they were just doing. This is the way the curve for the exponential distribution looks. It's curving downward, as you can see, because the probabilities are falling off very quickly for the larger numbers. Anyway, so now we can go ahead and think about what's coming next, chapter 7. Now, as it turns out, chapter 7 is heavily based on the normal distribution. Okay, so since it's fresh in our memories, that helps enormously. We're going to introduce some new concepts, but ultimately our examples will be based on the normal distribution. So this will be a relatively simple, well, I shouldn't say that. It's not like the longest or most intense chapter, let's put it that way, since we already know how the normal distribution works. But it does introduce some important new concepts. All right, so the next time we meet, we'll go through this. And if there's time, we'll start chapter 8, which is our discussion about something called confidence intervals, okay, where we get to learn about a brand new probability distribution. So in the meantime, we'll stop right now. We're done with 6. We still have 7 and 8 to go, and then we'll be done with all the new material. Okay, so I will see you then.